Short day, okay.
Okay, so I guess I'll start. I'm Glorielly, and I will be presenting to you my work on evaluating the indoor air quality at Lawrence University. So today we will be discussing what are indoor air pollutants, how does indoor air pollutants affect us, some background on COVID, and then that'll lead us into discussion of mask efficacy and social distancing, and then how to get rid of these indoor air pollutants, how to monitor air pollutants, and then we will conclude with, are we safe at the spaces on campus? So first, I'd like to start with a quote from the EPA, and they say that indoor air quality is up to 100 times more polluted than outdoor air. Now, how can that be? We're always talking about outdoor air pollution, like smog, and cities are really dirty, like the air is really dirty, but we don't really talk about indoor air. So I have this diagram to illustrate why that is. So in the pollution outside, so this orange cloud is representing pollution. Outside, the pollution is kind of dispersed through all the air and all the globe. So it's not as concentrated as if the pollution is indoors and the pollution is stuck inside our homes or some kind of building. It's very much concentrated. And so that's why the EPA says that indoor air is up to 100 times more polluted than outdoor air. So that leads to the question, how does indoor air become so polluted? The first thing is that any outdoor air pollution can come inside our homes, and then that'll pollute our indoor air. Another thing, so that's the outside things, but there are things within our homes that can contribute to pollution. And so the first thing is VOCs. VOCs stand for volatile organic compounds, and so that is the things inside of your homes. They are emitting chemicals, and then those pollute your air. So things that would emit VOCs include the carpets, upholstery, wall paint, perfumes and hairspray, in your kitchen, stoves, and cleaning chemicals. And why we even care that these VOCs are in the air is because they have impact on our health. So we have short-term exposure of just like breathing it and then immediately feeling some symptoms. And so those short-term exposures include dizziness, headaches, skin irritation, nausea, your eyes and nose and throat might get itchy, and you could irritate your asthma symptoms. So to illustrate, maybe you walk into a room that just got freshly cleaned with Lysol and it like makes your throat really scratchy, or it's like irritating because all of that Lysol is in the air. That would be the VOCs. And then there are some long-term exposures as well. Being exposed to chemicals in the air over a long time could cause things like cancer, heart disease, respiratory problems, lung and liver disease, and even affect the central nervous system. And now, while VOCs are important in considering indoor air pollution, it's not the only. I will not continue to talk about them anymore. I care more about particulate matter, abbreviated PM. And so particulate matter is teeny tiny particles in the air, and they are a mixture of solids and liquids. Things that contribute to the pollution of particulate matter include dust mites, mold, mildew, animal fur, smoke, and pathogens. I care most about pathogens, but let me first broadly tell you why particulate matter in the air can impact your health. So, breathing in this particulate matter can cause eye disease, digestive disorders, respiratory disorders, circulatory diseases, cancer, and allergies. During the springtime, when all of the trees are releasing pollen, when that pollution comes inside, your eyes might get itchy because of your allergies, and that's the particulate matter that is polluting your indoor air. So that is all the things within our homes and the things outside that can pollute our indoor air. But we also contribute to the pollution of our indoor air. When we breathe out particulate matter and CO2. And the particulate matter that we breathe out is separated into two categories. We have droplets, which are bigger in size. They're 5 microns or bigger in diameter. And when we breathe those out, they fall 1 to 2 meters in front of us. And then we have aerosols. Those are 5 microns or smaller in diameter. And due to their size, they fall further, 7 to 8 meters. And so that picture might have reminded you of aerosol transmission of COVID. I conveniently put 2 other people on the other side of the screen for where the droplets are falling. The aerosols. So I would like to get into a discussion of COVID-19 and how it fits into my research. So first, I'd like to give some background on COVID. What the heck is this spiky thing? That's COVID. It's coronavirus. It's got these little spike proteins, which I will describe to you what their function is. But first, I want to focus on the size of coronavirus. It is 0.1 microns in diameter. And so if you remember, I said that we breathe out droplets and aerosols, and droplets are 5 microns or bigger in diameter, and aerosols are 5 microns and smaller. So you can only imagine that a lot of coronavirus particles fit on our droplets and a little less on our aerosols. So to compare the size, I have a diagram. This teeny tiny dot here that you may or may not be able to see, that is the size of a coronavirus particle in comparison to other things. So a human hair, just one strand, the diameter of that is about 100 microns. A skin cell is about 30 microns. We have our 0.1 micron coronavirus, and then the droplet, that this one in particular is 10 microns. So you can only imagine that a lot of these fit on the droplets that we breathe out. So how does that fit into airborne transmission of COVID? Well, we get back to, we breathe out droplets, and these droplets contain a lot of coronavirus particles. And when the droplets that we breathe out, they fall 1 to 2 meters in front of us. The aerosols that we breathe also contain a lot less coronavirus than the droplets, but they also can contain coronavirus particles. And those fall 7 to 8 meters. So what can we do to help stop the spread of airborne transmission? First, we can abide to the 6-foot distance. And so the 6-foot distance takes care of all of the droplets that we breathe out. 1 to 2 meters in front of us is approximately 6 to 8 feet. And so by staying 6 feet away, you are keeping yourself from the droplets that have the biggest viral load. But then we still have the aerosols that we breathe out. And so we can take care of those with masks. So there's different kinds of masks that you can wear. You can have homemade masks. And those have an efficacy of about 50%. So when you're using a homemade mask, 50% of the particles that you breathe out will get caught, and then 50% will go through. The smallest particles are the ones that are most likely to make it through, so those aerosols will go through. Surgical masks have an efficacy of about 70%. So 70% of the particles that you breathe out will get caught by the mask, and 30% will make through. And then KN95, as the name suggests, has an efficacy of 95. So we talked about its size and how coronavirus is easily transmitted through aerosols and droplets. But the other thing that I wanted to talk about is that it is easily mutable. And so we can kind of take a walk down memory lane of COVID. So we started with the wild type, the original strain. This was the one that started the whole pandemic in 2019. And before I can explain to you how Delta and Omicron became variants of concern and the dominant strains, I need to explain to you how coronavirus infects humans. So this spike protein that I mentioned briefly before is really important to how COVID-19 infects our human cells. One fun fact about coronavirus is that when scientists discovered the structure of coronavirus and they saw these spike proteins, they kind of thought it looked like a crown, and so that's why it got the name coronavirus. And so these little spiky things called the spike protein, when coronavirus gets into yourself, these spike proteins, well, first let me say, this yellow part is the cell surface of a human cell. So the coronavirus particle will come and it'll kind of handhold with our human cells. And so in doing that, coronavirus has made a bond with our human cells. Once it makes that bond, it is able to fuse, which is what is happening here. We see the surface of our human cell, the surface of our human cell, and it is fusing with the coronavirus, and it is able to inject its genetic material into our cells, and then it can make more of itself after doing that. And so this spike protein is really important to how coronavirus infects us. And why I even bother telling you that is that from the original wild type to Delta, Delta had some mutations in its genetic material that made its spike protein better at hand-holding than the original wild type. So Delta became the dominant strain in June 2021 because its spike protein was better at hand-holding, or better at latching onto our human cells, and so that's why so many people were able to get infected with Delta, because it was just more efficient at infecting people. And then we have Omicron. And so Omicron, it became the dominant strain a little bit later in that year, in November 2021, and it had approximately 60 mutations. And what was different about Omicron spike protein is that it evaded the immune system. Its spike protein hid all of the parts that our immune system was good at recognizing as foreign, and so instead our immune system saw Omicron, was like, you're probably okay, and it didn't attack it immediately. And so that's how Omicron became the dominant strain in 2021. So now that I've told you guys a lot about coronavirus and ways that we personally can stop it from getting into the air, I want to show a bigger picture of how we can get coronavirus out of the air. And so if we're social distancing and wearing our masks, there's still the possibility of particles making it through our masks. So how do we get rid of any contaminated air after that? And so the easiest and cheapest way to do that is to open a window. The particles that we breathe out will just flow out the window, but that's not always possible. For example, in this room, there are no windows that we could open. If you're in a tall skyscraper, the windows don't open, and most of sites, the windows don't open there either. So in those situations, you have to introduce ventilation, and so that is when you mechanically push out any old air, or in this case, infected air, and replace it with fresh air from the outside. But it is really expensive to do a 100% exchange of pushing out all of the old contaminated air and 100 replacing it with fresh air, so you have to recirculate. And so how recirculation works is that the particles that we breathe out, they will make it through a filter. On campus, we have MERV 13 filters, and those are very good at catching even the smallest particles. So they'll pass through the filter, and the filter will catch as much particulate matter as possible. But what doesn't get caught is What doesn't get caught is CO2. And some of the teeniest, tiniest particles that might have one coronavirus particle may make it through the filter. So if CO2 is able to make it through the filter, and that means that we can use CO2 to approximate the ventilation rate, because if the ventilation isn't keeping up with all of the CO2 in the room, then the CO2 can accumulate. I will show a diagram of how we can use CO2 to approximate ventilation. So in an empty room, we have a baseline CO2 of approximately 450 parts per million, or ppm. When people enter a space, the CO2 levels rise as long as the ventilation rate stays the same, because the ventilation can't keep up with the extra amount of CO2 in the room. Then we will reach a steady state where the amount of CO2 is pushed out as much as possible from the ventilation, but because there's more people in the room, we can't ever bring it back to base level. And so we need to bring the CO2 level down, and there are 3 ways that we can do that. The first way is to increase the ventilation rate. If we increase the ventilation rate, then more of that old infected air will come out and fresh air can come in. Or people could leave and the CO2 level could slowly decrease. Or a third option is a combination of the two, where we increase the ventilation rate and people leave. Now, I gave you all of that information about how do you know that I am giving you truth. So I monitored the air using these aware sensors. They've been all across campus. And these little alarm clock looking things, they collect information on particulate matter, CO2 levels, which I care about, but they also collect information on VOCs, temperature, and humidity. So I use the particulate matter and the CO2 readings to determine whether the air at Lawrence was safe for us. And so before I show you any data, I want to say that we hypothesized that the efforts made by facility services, the Lawrence Pandemic Planning Team, and all students, faculty, and staff were enough to lower the chance of getting coronavirus. So let's see if what I told you held true. First, we can look at the CO2, and if you remember this graph that I showed you literally a minute ago, and how we can use CO2 to approximate ventilation, you'll see that that shape still holds true in this CO2 graph. So this is taken from one of my sensors that was placed in an office in Brokaw. And so I just grabbed a week. We have Monday, Tuesday, Wednesday, Thursday, and Friday. That's what all of those peaks represent. And they still have that trapezoidal-like shape. So on Monday, it looks like some people came into the office. And then around noon, they had a lunch. So that's why the CO2 level dropped a bit. They came back, and then when they left for the day, the CO2 level came back to its baseline of around 420. And then the next day, people came in, and there's the same sort of pattern. On Wednesday, the peak is higher, and to me, this seems like more people came into the space, and so that's why our peak is a bit higher. Thursday, we see a similar thing, that the peak is almost as high as Wednesday, so more people were in the office on Thursday compared to Monday and Tuesday. And then Friday, the peak is the lowest, so less people were in the office, and then we see a larger dip, which means people were probably taking a longer lunch on Friday, and then they left for the week. So the CO2 is behaving as we expected, which means we can go on and see our other assumptions and try to approximate the ventilation. Before I show you some more graphs, I wanted to say that the following graphs I created in R, and so this is my code. To explain my code just very briefly, I have a graph for particulate matter and another one for CO2, and I took 15-minute averages, so my sensor took readings every 5 minutes. So I took those readings and averaged them in 15-minute groups so that my graphs don't look so busy, but they still look kind of busy. So here's the first one, and so I'm going to use this graph to try and answer what did the CO2 say about our ventilation rate. So first I have this red line. Well, actually, let's see. The data in this graph is taken from the Commons during the 2020-2021 academic year. And so I chose the Commons to answer this question because the Commons is our dining space on Lawrence. It's one of the most used spaces on campus. So if anywhere is going to be dangerous, the Commons is probably the best bet. So next, we have CO2 on the y-axis, and then I have this red line. And what this red line is representing is when the CO2 levels are dangerous. And so if they were to pass this line, then we would probably be worried about too much admission from people's breathing. But since the CO2 never reached that line, we can confirm that the ventilation rate is high enough that we're reducing the risk of COVID. Now, if I explain the behavior of the CO2 in this graph, first, this is fall term. These peaks still represent mealtime, so more people are in the Commons, and that's why we're getting these peaks. we see a dip here, and this dip is winter break, so there are less people on campus, which means the CO2 level is going to go down. And then this is slightly higher because this is winter term. In the winter, our ventilation rate is slightly slower because it is very cold outside. So when we're pushing in fresh air from the outside, we need to warm it up and then bring it into our space. So that's why our ventilation rate is slower. So to conclude, yes, our ventilation rate is high enough to to reduce the risk of COVID. But that's still, we still need to know about the particulate matter. Was the particulate matter levels low enough for COVID to reduce the risk of COVID? And so I have this red line, and again, this line represents what would be dangerous levels of particulate matter. And for the most part, throughout the school year, again, I'm looking at the commons in the 2020-2021 academic year. For the most part, we kept our CO2 levels down, but then something really bad happened in the spring term. Like really, really bad, because these dots are much higher than this red line. And so if we zoom in to spring term, now I'm taking the points and I'm separating them by the weeks in spring term, and then I'm color coding by what AWARE told me are different categories of particulate matter levels, and so it gave me a range of healthy through poor. And so towards the end of spring term, we were reaching far into the poor range. And you'll notice that there is a cluster of points up here, and that is because my AWARE sensor only reads to about 1,000 ppm. So we were maxing out the sensor at this point, and there's most likely even higher particulate matter levels than at 1,000, but my sensor couldn't tell me. And so what did happen during this time? Well, we figured it couldn't be students, because if it were students, then we should have seen that the CO2 levels rising at like dangerous levels, but they never were. They stayed pretty consistent. So then we asked Joseph King, the director of facility services, if there was any construction happening at the time. And there was construction happening at the time. All of the dirt and debris that comes up during construction, my sensor was picking it up, and so that is why there are dangerous levels of particulate matter in the spring term. So what we conclude from this graph is that you should probably stay away from construction sites. But if you can't, try to wear a mask so you're not breathing in all of that particulate matter. So if we go back to the graph I showed before and we exclude all of the construction, then does it look like particulate matter was low enough to reduce the risk of COVID? And I would say yes. All of the points are well below the red line, except for the construction. So yes, throughout the school year, our particulate matter was low enough. Okay. But there's more. As Deanna was saying, people really want numbers to feel reassured that the spaces that they're in, we are safe. And so right now, I'm trying to use this model that I found from, this model was presented to me during one of my interviews, and it is made by a scientist at MIT, and he is trying to calculate your probability of getting coronavirus given certain parameters. And so there are two ways I could use this model. I could use it the really complicated way, which I'm still trying to calculate all the things I need. And so to do it the complicated way, I would need to know what the dominant strain was at the time, because different strains have different infectivity rates. I would need to know what masking was happening, the size of the room, the baseline CO2, and much more parameters. But I'm still trying to gather all of those parameters, so I can't do it the complicated way just yet, but Deanna and I are working really hard to get those numbers for you by the end of the term. The easier way to do it is to use the baseline CO2 levels to approximate what your risk of COVID is in a certain time. So I will go through a demonstration of how we can do that. We can go back to our Brocadt example. And so if you look at this graph, we have a baseline of about 420. I just approximated the overall average. And so I plugged that into the model. And what it's telling me, so I put the background levels of 420. And first, let's look at this graph. So on the x-axis, we have the maximum exposure time. And so what that means is just how long that you've been in a given space for. And then the y-axis is CO2 in parts per million. This red line denotes when it would be dangerous. And for the purposes of this example, I used a 10% risk of getting COVID as being dangerous. I know we all have personal definitions of what we consider to be dangerous, but I just used 10% in this example. And so if we get into this region of the graph, then we would be dangerous. So it gives me some generic calculations. For example, if I was in a given space for 8 hours, the CO2 would need to be greater than 2,000 ppm to be dangerous. Or, and another way we could say that is for CO2 concentrations of 470, which was, if I go back to this graph, is the highest that, well, we didn't even reach that, but if it was higher than 470, then we would need to be in a space for 14 days before we reach that threshold of a 10% chance of getting COVID. So from this calculator, from this calculator, we can conclude that the people in Brokaw were safe and they most likely didn't get COVID from being in these spaces. Okay, and that's all I have for you guys. I'd like to thank Deanna Donahue for being my advisor and helping me throughout the summer and throughout all of this academic year, and for moving the sensors around campus. I really appreciate that you did that. And then I'd like to thank Joseph Kingman, the Director of Facility Services, for giving me a job over the summer and for answering all the questions that I needed to do my research. And then I'd like to thank all of the students here who have given me feedback and, given me support when I get really stressed. So thank you so much. And now I'll take questions.
Okay, Glorielly is ready to take your questions. Who's got them? Ezra.
Yeah, so you said that your sensors, there was like one slide where your sensors maxed out at like 1,000 of the 2.5 year, right? Do you think it would be beneficial to run the experiments that you ran with a sensor that didn't max out at 1,000? Like, would that offer any additional information, or do you think your data as is adequate?
I mean, we could put those sensors, but since it's already past that unhealthy, it might not be any more beneficial to get the exact reading of what 1,000 is, because from 35 to 1,000, that's like way, way unhealthy.
Just to be clear, this was actual construction in the vents at times, and so that really could make an impact on where we put the sensor. So it was pretty specific type of construction too.
Got it.
I think I saw Justin had a question.
Yeah. How do you think that this could potentially interact with other forms of particulate matter? Like, could it potentially attach to larger particulate matter and deposit out faster than we thought?
I'm not understanding your question.
So like if you go back to your slide that like has like all the different types of particulate matter inside, like would it potentially interact?
This is a aerosol microphysics thing, so maybe I'll grab it back from you, Glorielly.
Cool.
They're in general much bigger than you would get from in the conglomeration phase. So at a certain size, they don't actually conglomerate into larger particles. We're already sort of on that upper end. This is a whole different mechanism of formation. So they're big already, so they'll have to fall out by gravity mostly.
Okay.
Some of the tiniest ones will, but more fall out than conglomerate.
Yes.
So it's a slide where you talk about how given enough time, like the amount of CO2 would build up if a human is staying there for a long enough time, right? So what if like the room would just shut down and there's no filtering of air, or you don't open the window and there's no ventilation, and then at some point, like I don't know, 100 days later, you just inject a human in. Would that be like really bad in terms of air quality as well? Like I don't know.
I mean, I wouldn't know everything that's happening in that room, but I would think if it was closed and there was a way for stuff to collect into the room, then yeah, the pollution would build up in that room.
Like just like a storage room.
Yeah.
Yes, Allison.
Did you have to take into account humidity? And I just know that the buildings normally go through crazy changes from summer to fall to winter. And I was just curious if you incorporated that into your data analysis.
Right now, no. We did think about it though. We had lots of discussions about how we could think about humidity, but for the first part, it was just easier to forget about the humidity and then factor it in. For this model, they do ask for the humidity at the time, so when I get those numbers, I will be factoring
Yeah, that's a
humidity.
hard problem to figure out.
Yeah.
Cool.
Other questions? Yes, back there.
So you had mentioned that the data was from last year's school year. How do you think that the data from the commons would compare to this year, where we have more students dining in the commons along with more faculty back, compared to last year where there was very limited dining to almost no dining?
So are you asking, like, how does the data compare?
Yeah, like how do you think it would compare, like now versus then? Do you think we'd still be at safe levels, or would the data be changed?
I think we would still be at safe levels. I do think that the relative CO2 level will increase and the particulate matter would increase a bit too, but I do think it would still stay below the threshold.
Any other questions for our speaker? Okay, let's thank our speaker one more time. Thank you for joining us. The next talk is on Friday at 3:10.
Oh my God.
The people contest.
Yeah.
Great job.
Bye, guys.